Hello, I'm Stuart Reid. Welcome to this course on AI testing. In this session, I'll cover some of the quality characteristics that are especially important for AI-based systems, such as flexibility, adaptability, autonomy, and evolution. ISO 25010, part of the ISO 25000 series, is an ideal starting place for considering quality characteristics, as it defines a product quality model applicable to any software system, and thus also to any AI-based system. However, not all of the listed characteristics will apply to all systems. For instance, compatibility may not apply to standalone embedded systems, and usability will seldom apply to those systems with no user interfaces. In practice, it is best to check each of the characteristics and discard those that are not relevant, rather than accidentally miss an important characteristic. The slide highlights that each of the listed quality characteristics, other than functionality, are used as the basis for non-functional testing, with the functional characteristics forming the basis for the functional testing. The presented quality model is generic, and so it is applicable to any software system. However, in this section, we will extend this model to introduce additional quality characteristics that are specifically applicable to AI-based systems. At present, ISO are working on ISO 25059, which will be a new standard in the ISO 25000 series, and this new standard, when published, will exclusively cover AI-specific quality characteristics, which should be similar to those we cover in this section. On this slide, we can see a list of the AI-specific quality characteristics covered by the syllabus. In this session, we will cover the first four listed: flexibility, adaptability, autonomy, and evolution. We will cover the remaining characteristics, which are greyed out on the slide, in subsequent sessions. Each will be covered in turn. We will consider the flexibility and adaptability of AI-based systems together, as they are very similar concepts. Both are concerned with the system coping with new situations. Flexibility is an intrinsic characteristic of a system being able to cope with new situations itself. Slightly different is adaptability, which is concerned with the ease of someone else changing a system to manage these new situations. As we can see from the definitions, flexibility is built into a system and requires no further human effort, while adaptability is a system attribute that defines how easily humans can modify the system. On this slide, we consider typical situations that would encourage us to prioritise flexibility, adaptability, or both in a system. Both are concerned with the ability of a system to deal with operational environments and situations that may not have been fully understood or predicted when the system was designed. In such a case, we want the system to either be flexible enough to cope with the unexpected situations itself, or adaptable enough so that it is easy for maintainers to update it to cope with a new situation. A specific attribute of a flexible system is its ability to identify those cases when it needs to employ its built-in flexibility. For instance, a system that changes modes based on weather conditions must be able to identify all possible changes in weather that it should respond to, and ideally, it should recognise relevant weather changes that do occur as early as possible. Flexibility is also of specific interest when we talk about self-learning systems. Many people believe that all AI-based systems are self-learning, but this is not the case. For many systems, machine learning is used to build a model from the training data, and the resultant model that is deployed is stable and does not change once the system begins to be used operationally. This is the case when machine learning is used for safety-related systems. We do not trust that a flexible system will always change itself in a way that leaves it safe, and so self-learning systems are not used for safety-related applications. Having said that, self-learning systems that modify and improve themselves based on their experiences are a really useful subset of AI-based systems, and in the future are likely to be more widespread. However, building self-learning into a system is necessarily more complex, and so it increases the risk of the system failing. Thus, the decision to use self-learning systems is a compromise between their potential improved performance, which is achieved through the system's built-in flexibility, and the increased risk this complexity brings. Today, commercial, non-safety related self-learning systems are available and are used in some mission-critical situations where the ability to improve from self-learning is considered important enough. For instance, there are examples of self-learning systems that work with financial markets and have a requirement to change in response to what happens in these markets. Normally, this is when the changes have to be made more quickly than they could be if the changes were made manually. When specifying requirements for flexibility and adaptability, there are two main considerations that have to be agreed and documented. First, we need to specify the extent to which the operational environment is expected to change. For instance, we may expect a self-learning trading system to automatically respond to market fluctuations that average up to 25% across the whole market, but not when this figure is exceeded. Second, we need to specify how much effort should be expended by the system in coping with expected or unexpected environmental changes. This effort may be expended by the system itself, if we are talking about flexibility, or by those modifying the system if we are talking about adaptability. For instance, for adaptability, we could set a maximum number of person hours to be spent in replacing the current set of sensors with a new sensor upgrade. Or, for flexibility, we could specify the maximum time allowed for a heating system to respond properly when a new person starts living in the space it is responsible for heating. Autonomy is a system characteristic that many of us immediately associate with AI-based systems. This slide shows just a small selection of the wide range of autonomous systems that are in use today. Autonomous systems can be physical, for instance intelligent robots, or purely digital, such as software agents making trades on financial markets. Obviously, most of the examples shown here are physical systems, as they are more photogenic, but the financial trading system shown on the right is not a physical system. Sectors where autonomous systems are widely used include transportation, and we can see 4 examples of this on the slide with self-driving cars, submersibles, drones, and a passenger shuttle. Robotics and the Internet of Things are also areas where many autonomous systems are found, and the robot mower and tractors provide examples in this area. Other areas where autonomous systems are used, but not shown here, include manufacturing, vacuum cleaners, smart thermostats, medical diagnostics, smart buildings and smart cities, to name but a few. Autonomy is notoriously difficult to define, especially because autonomous systems are rarely ever fully autonomous, in that they have full control of what they do with zero oversight. Instead, we use the definition provided here that allows autonomy to be defined in terms of periods of activity with no human intervention. Note that this definition does not require the system to include any AI, but we will see later that including AI components can be useful for some autonomous systems. Self-driving cars is an area where there has been much debate about what is meant by autonomy. The current status is that cars are not officially described as autonomous. Instead, they are rather defined as having one of 5 different levels of automation, with level 5 being as close to fully autonomous as cars can be. For such cars, an example at level 4 would be a driverless taxi that worked within set geographical limits, such as a small city. As a passenger, you would have no responsibility for the driving, but the taxi might stop safely before your requested destination if certain conditions applied, such as freak weather or a collapsed bridge. At level 5, a car would just need a destination and could take you anywhere a car could reasonably go, with no other inputs required from you as a passenger, so allowing you to sleep, drink, or party as you travelled. At level 3, there must be a human driver who is able to take control if needed, but the car can drive itself in limited situations, such as driving in traffic jams on dual carriageways. Audi developed a level 3 car back in 2019, which provides traffic jam assistance and uses AI to make decisions. However, it was never approved by the German regulator. Since then, in 2021, Honda have gained regulatory approval for their Legend sedan to provide traffic jam assistance, but only in Japan. Autonomy requirements can be specified from two perspectives. First, how long the system should work without human intervention, and second, what should cause the system to relinquish autonomy back to its human controllers. Note that this second requirement would not be necessary for a level 5 car, but it is unlikely that a level 5 car will be possible before we achieve general AI. This slide shows the high-level structure of a generic autonomous system. The system gathers information through sensors or input channels, and then needs to make sense of the gathered information. Next, the system needs to decide what to do based on this information. And finally, the decision needs to be put into action by the control component. It does this by interacting with the real world through actuators or output channels. As is shown, an autonomous system can include AI to varying extents. In some simple autonomous systems, such as basic thermostats, none of the functions are implemented using AI. Whereas more complex autonomous systems may use AI to support all three of the shown functions: sensing, decision-making, and control. If we consider this model in the context of self-driving cars, then sensing and decision-making are often implemented using AI, normally in the form of deep neural nets. However, control, such as managing the engine and brake components, is still often implemented using non-AI components. We already considered the need for flexibility in self-learning systems. Here we look at the ability of systems to evolve and how this is inextricably linked with self-learning. System evolution is defined as the system's ability to improve itself in response to external constraints. Ideally, such changes should improve the system's efficiency, effectiveness, or both. A self-learning system can learn from changes in the operational environment, such as climate change, and also from the effects of its own decisions and actions, such as with reinforcement learning, which we will cover in detail later in the course. Requirements for system evolution need to constrain the amount of change that the system can make to itself. For instance, not allowing changes to the system that would cause it to exhibit new unwanted characteristics, and of course ensuring the system's core requirements are still provided. These constraints will need to be specifically identified and the level of acceptable change defined for each relevant characteristic. These characteristics also need to cover how the permitted evolution is allowed to affect day-to-day human values, such as not causing harm to people, the environment, or animals. A major problem in specifying such requirements is that there is not normally a generally agreed definition of human values, because different cultures often have quite different values. For instance, some people seem to value the life of a pet more highly than the life of a person, as we will see later when we cover ethics. This has been the session in which I presented an introduction to some of those quality characteristics that are especially associated with AI-based systems, including flexibility, adaptability, autonomy, and evolution. Thank you for listening, and I look forward to seeing you next time.